Hi, everyone. We'll just get started here in about a minute or so. I just want to give people some time to filter in. Thanks for joining us. And if you'd like, go ahead and put in the chat box where you're tuning in from today. We love to know where everyone's located. Ooh, Athens, Alabama. Someone from down south. Chicago. I used to live there. It's probably pretty cold right now. Tulsa, Dallas, Miami, all over the place.
Hi, Leslie. I'm Tulsa too.
Oh, nice. Fort Lauderdale. All right, we've got a good number of people logged in already, so I think I can go ahead and get us started. Hi, everyone. My name is Catherine Swery, and I am the Content Marketing Specialist here at ACHS. Thank you all for joining us today for today's webinar about senolytics. Oh my goodness, tongue twister with Dr. Andrea Price. Before we get started, I just have a few housekeeping items. You may have noticed that your line has been muted. We are recording today's webinar, and this helps us to ensure better sound quality for everyone who views the recording later. If you have any questions or comments during the presentation, please go ahead and put those right in the chat box at any time. We have Dr. Patricia Kaufman on this webinar as well, our Dean of Integrative Health and Nutrition, and she will be in the background monitoring the chat, helping to answer any questions. One thing I do want to note about the chat box, you'll see that there's a blue drop-down button, and you want to make sure that that is set to everyone so that everyone can see your questions and your comments throughout the webinar. Um, so yeah, and then go ahead and switch to the next slide, please, Patricia. I'll just go over a few more items. Thank you. So at the start of our webinars, we generally like to share a bit about ACHS. We specialize in online distance education and have been accredited by the Distance Education Accrediting Commission since 2003. We are also a certified B Corporation, which means a huge part of our mission is advancing and supporting sustainable communities and sustainable practices. And we offer a range of programs, including accredited certificates, diplomas, degrees, micro-credentials, and on-demand continuing education. And you can learn more about this on our by visiting our website, achs.edu, or send us any questions in the chat or via email afterwards. So with that, I will go ahead and hand it off to Dr. Price to get the presentation started.
Hey, hi everybody. My name is Dr. Andrea Price. I'm a professor here in the Integrative Health Nutrition department, teaching both in undergraduate and graduate. I have a lot of experience in the field of integrative health. I've worked in supplements and in clinical medicine all over the place. And science is really something that is near and dear to my heart. So I wanted to bring this to you guys today because it's something kind of unique and something that can make a big difference for people, but it's not something that's super well known, but is definitely up and coming. So today we're going to talk about senolytics and cellular senescence, aging, and kind of how all that works together. Next slide, please. So, yep, there's me. I'm a naturopathic physician by training, health educator, longevity science enthusiast. So one of my biggest things that I love doing is taking complex stuff and translating it into kind of practical real life strategies so that, can help both professionals and clients, everyday people make smarter, more confident decisions about their health. Next slide, please. All right. So today we're going to have a talk about one of the most, really exciting frontiers in longevity science. And this is something that really moves us away from kind of managing symptoms of aging and moves us towards addressing one of the fundamental drivers of that aging process. So, here's the thing about getting older. It's not just that our cells kind of deteriorate and don't function as well as they used to do. It's that they stop dying when they're supposed to. And when cells that should be dead aren't, that's when the trouble, really starts. So we're going to talk today about this, growing toolkit that we have of natural compounds that help our bodies clean up all of this cellular mess. This isn't a replacement for those basic habits, those foundational things, sleep, exercise, nutrition, but this is a very precise, targeted intervention that addresses one specific hallmark of aging. So, our goal today is to understand not just what senolytics are, but how they work, why the evidence is, compelling and still evolving in that field, and how we can intelligently talk about them and use them, with clients with confidence. So we're going to start off with the question of, what if the cells causing the most damage in your body aren't the ones that are actively growing or multiplying, but the ones that have completely stopped? So that's kind of what we're starting at today. Next slide, please. So we've got a cell that now is no longer dividing. It's metabolically, quiet. And that's what happens after it's made that choice of senescence. Senescence sounds like something super, clinical, kind of almost coldish in a way, but what it's really talking about is a cellular, decision point. And understanding this decision is really foundational when it comes to everything else, longevity science. So, here's the story that we're, kind of imagining here. So a cell encounters some kind of serious stress. Maybe its DNA gets damaged from UV radiation or oxidative stress, or just, general wear and tear accumulation over time. Maybe it's telomeres, those little caps on the end of the chromosomes have gotten too short and they're starting to unravel and fray. This makes the cell's internal alarm start going off. Oh no, I'm damaged. Help, help. It's got to make a decision. It can either keep dividing as a damaged cell and risk becoming cancerous, or it can stop dividing forever, kind of the kamikaze move. And this is cellular senescence. It's actually a very brilliant protective mechanism. The cell says, I'm too damaged, not going to multiply anymore, because if I do, I could become a tumor and kill off the whole organism. So for a long time, maybe even most of an organism's life, this is a good thing, right? It's cancer prevention. It's protecting us. And, by the technical definition, cellular senescence is an irreversible growth arrest that's triggered by these stressors, like the telomere shortening, the DNA damage, mitochondrial dysfunction, even things like impaired autophagy, can result in senescent cells. And when that growth switches on and, the cell stops cycling. But, this is the really crucial part. It just doesn't die. It just stops doing all the cell stuff. And again, initially protective. This is our firewall against cancer. But, the problem that we're going to talk about today is what happens when these protective, non-dividing cells kind of wear out their welcome and stick around too long. And that's where kind of the real story of aging begins. So when we're conceptualizing senescence, it's important to recognize that it's not a disease state per se. It's a protective mechanism that has outlived its usefulness, like inflammation or any of those kinds of things. The goal with senescence isn't to cut it out entirely. We don't want to completely prevent it. We don't want cancer, but the goal is to, clear out those senescent cells once they've done their job and are starting to cause harm. Next slide, please. So, once that's happened, it's a metabolically quiet cell, or so we thought. But, in the 90s, researchers made a huge discovery and found out that these senescent cells aren't just sitting there la-di-da-di. dormant, doing nothing, hanging out. They're actually still doing a lot of things. And many of those things are extremely problematic to the organism overall. So this, is where the term kind of zombie cells comes from. I know that sounds super, hyperbolic, but it's, actually extremely accurate and probably the best way to describe these cells because they are biologically dead in one sense. They can't divide. They're, but they're kind of still metabolically active, still secreting, still influencing their microenvironment. And, when a cell becomes senescent, it activates something called SCAPs, SCAPS. These are senescent cell anti-apoptotic pathways. And we can kind of think of these guys as a cell's sort of pro-survival shield. It's the cell really saying, I'm going to divide, but I ain't going to die either. So the cell turns on these anti-apoptotic pathways, particularly ones like PI3K, AKT, mTOR axis, and also the BCL2 family of proteins. And all of these things block the normal apoptosis death signals to the cell that would typically tell an old or damaged cell, it's okay, go ahead and die off, end of watch, we got you. But, why does a cell do this? Like, why wouldn't it just die off? Why would it try to stay alive? And, kind of one of the theories behind that is really an evolutionary logic. If you're a damaged cell, that stop dividing to protect the organism, your best strategy is to hang on and keep signaling, I need help, I need help, I need help, in case you might still be useful to the organism. But this hanging on is exactly what is becoming problematic for the organism. So the key point here is that senescent cells are actively resisting death. They've upregulated these pro-survival machineries, specifically to prevent apoptosis. And this is the Achilles heel that we're going to talk about with senolytics and, where we can exploit that to impact these senescent cells. So when, we're thinking about these cells, we're not forcing cells to die prematurely. We're disabling these specific survival shields that are preventing them from dying when they should. And that's why senolytics have selectivity. Healthy cells don't rely on these hyperactivated pathways the same way that senescent cells do. Next slide, please. So here is the point where the story gets a little bit darker, but also more interesting. So if senescent cells just sat quietly in our tissues, their hands folded in their lap, and did nothing, crisscross applesauce, refusing to die, refusing to divide, that would actually probably be pretty fine, like no problem. But the problem is that they don't, right? They're like, neighbors blasting music at 2 a.m. and, throwing their garbage over the fence into your yard. In the early 2000s, researchers discovered something extremely remarkable about senescent cells, and that is that they do actively secrete compounds, lots of them, hundreds of different molecules come from them. And what are these molecules? Primarily inflammatory signals. Pro-inflammatory signals. And they actually have a name, the whole group of them. They're called SASP, SASP, that's senescence-associated secretory phenotype. And this is one of the most important concepts in modern aging biology. So we're going to break this down and talk about it a little more specifically. So SASP includes 3 categories of molecules. It includes the inflammatory cytokines and chemokines. These are molecules like our interleukin-6, interleukin-8, TNF-alpha, MCP-1, classical inflammatory signals. These tell all the other cells, something's wrong here, bring the inflammation, we need to fix this. We also have our MMPs, number 2, matrix degrading proteinases. And these are enzymes that literally break down the structural proteins in the extracellular matrix. So collagen, elastin, other structural proteins that are in that extracellular matrix, gone. MMPs chew right through them. And this is why senescent cells in connective tissues can drive tissue dysfunction, accelerate aging, skin, joints, organs, all of that because of this effect on the extracellular matrix. Number 3 are the bioactive growth factors. So these would be molecules like VEGF, HGF, that, well, sometimes trying to be helpful can actually promote things like fibrosis, aberrant angiogenesis, so building blood vessels where we don't need them, and other kind of maladaptive tissue changes. But the really important part of all of this is that this secretion is not a bug, it's a feature. The senescent cell thinks it's helping. It's trying to signal, I'm damaged, send help. Maybe the immune system can come help me and clean me up. But what actually happens is chronic low-grade inflammation. And most people have probably heard it termed as inflammaging. That's what's going on here. But unfortunately, that's not the end of the story. It actually gets worse. Those inflammatory signals from senescent cells can actually push neighboring healthy cells into senescence themselves too. So you actually get this spreading wave of cellular dysfunction around that one zombie cell. So one zombie cell becomes a whole neighborhood of zombies, which becomes a district, and the vicious cycle on and on and on. So when we see chronic inflammation showing up in clients, if we see an elevated CRP, interleukin-6, TNF alpha, one source of that information is literally these senescent cells screaming these pro-inflammatory signals from the tissues. Senolytics don't just prevent this senescence accumulation, they potentially also reduce the systemic inflammation that's a driving factor behind multiple chronic diseases, particularly those associated with the aging process. Next slide, please. So one of the things I really want to kind of hammer home on this slide, because it's kind of that bridge between, that's cool, and that's why this is important in a clinical setting, is, that those senescent cells are not just sitting there passively doing nothing. They are actively degrading the surrounding tissue and driving systemic inflammation in the body. The SASP is essentially a cellular distress signal that when it's constantly happening due to accumulated senescent cell burden, it becomes pathological. So we think of inflammaging, that chronic, low-grade systemic inflammation increases with age as being partially driven by the SASP. We used to think inflammation in aging was mostly due to activation of the innate immune system or, kind of accumulated molecular damage, other drivers like that. And while those are also real, we now understand that SASP is also a significant contributor. So in actuality, what that SASP is doing is it's, degrading tissue structure via those MMPs. It's recruiting immune cells and creating a pro-inflammatory microenvironment. It's impacting wound healing, tissue regeneration, promoting fibrosis in organs, accelerating neurodegeneration in the brain, driving systemic metabolic dysfunction in general. So, the cycle becomes senescent cells get created, SASP starts going up, chronic inflammation starts going up, DNA damage, stress in neighboring cells, new senescence, more SASP, lather, rinse, repeat. We can see, it's that positive kind of feedback loop of aging. But the research is showing that clearing these cells, removing the source of that SASP can actually break that loop. And that's why the evidence from animal studies is so compelling, and why human trials are now underway with a lot of these things. Next slide, please. So now we get to the mechanistic kind of heart of why senolytics matter. And that is that this senescent cell burden increases with age. Here we're looking at two scenarios. In youth, there's a balance. Our body is creating senescent cells all the time, completely normal. This is protective senescence happening as a cancer prevention, mechanism in the body. But our immune system is also youthful and healthy and is able to clear out those cells efficiently. We're in homeostasis, senescent cell levels stay low and manageable. But as we get older, we see changes, and that graph kind of shifts. One side of the equation, senescent cell creation, increases. Why? Because we're experiencing more DNA damage, more oxidative stress, more telomere attrition. Aging equals more stressors equals more cells triggering senescence. And, that makes biological sense. But on the other side of the equation, immune clearance becomes less efficient. And this is partly because the immune system itself ages and becomes less effective. That's called immunosenescence. And it's partly because senescent cells actually suppress immune recognition. They secrete factors that impair immune clearance and things like that. It's a multi-dimensional, multi-directional problem. So the result, though, is that the balance tips. We go from, senolytic cells that we can clear easily, which is, a manageable state, to so many senescent cells that our immune system is overwhelmed, a pathological state. And that's when the senescent cell burden becomes a driver of the aging process. But the remarkable thing, though, research shows that when you experimentally clear out senescent cells in aged animals, either genetically or pharmaceutically, we see improvements in health span, fragility, frailty, organ function, even lifespan. So the implication is that the senescent cell burden is a tractable target for intervention, meaning it's not inevitable, it's actionable. And so, we're not discovering senolytics because we need another supplement to take. We're discovering them because they target a very specific tractable mechanisms that worsens with age. And unlike many aging interventions, this mechanism has an on and off switch. Either senescent cells are there or they aren't. Next slide, please. So we've mentioned senolytics a few times, but let's make sure we're all on the same page, with the definition, because language matters. So the word senolytic comes from two Latin words, senex, meaning old, and lysis, meaning destroying or breaking. So literally destroying or breaking old cells. The definition is a bit more specific than that. A senolytic is a compound that selectively targets senescent cells, not healthy cells. Remember, we talked about those SCAPs in the beginning and how healthy cells don't rely on those as heavily as the senescent cells do. It triggers apoptosis, that programs cell death in those senescent cells. It's not randomly killing cells that weren't already supposed to be dead. It works by disabling those pro-survival pathways that allow senescent cells to resist the death signals that are already being sent to them. So, in plain language, senescent cells upregulate those SCAP networks, those pro-survival pathways that block apoptosis signals. Senolytics work by interfering with these specific pathways. They essentially take away the cell's, do not die shield, and allow those normal apoptosis signals to get in there and do their job. And the really brilliant part about all of this is, again, those healthy cells don't rely on hyperactivated survival pathways. So senolytics have selectivity. They preferentially kill senescent cells while leaving healthy cells relatively unharmed. And this is the basis for their therapeutic potential, and also the reason that, we can think about, using them in a safe way. When we compare this to other things like, traditional cancer chemotherapy, very non-selective for the most part, it kills all rapidly dividing cells. So it damages healthy tissue too. And senolytics are different than that. They target specific cellular states of senescence via those SCAP networks, that are particularly relevant in the aging process. So, they work because they're selective. They're designed to kill cells that are already in a pathological growth arrested state. They don't indiscriminately trigger cell death in any random cell. So this is very, precision care that we're talking about here. Next slide, please. So remember I mentioned earlier that those SCAP networks are really the Achilles heel of the senescent cells. So this shows us kind of the visual story for how these senolytics actually work. So on the left, we see a senescent cell. This cell has been triggered to stop dividing. That's that growth arrest part. Now it's activated those pro-survival shields, those key SCAP networks, the PI3, AKT-mTOR axis. That's a major growth signaling pathway that, when it's overactivated in senescent cells, prevents apoptosis. We also have that BCL2 protein family. These are anti-apoptotic proteins that directly block the molecular machinery of cell death. So these pathways are basically saying, oh, ignore those death signals. I'm not going to die. And then in comes that senolytic molecule. And depending on which one it is, it might directly inhibit PI3 or AKT. It might block those BCL2 family proteins. It might disrupt other survival pathways. Or in some cases, it might even actively generate stress inside the senescent cell to cause it to self-destruct. But, in any effect, the survival shield collapses, the cell loses its resistance to apoptosis. Apoptosis signals that were being blocked can now go on and execute, and the cell will die off. The apoptosis signals on the right show a normal cell death pathway that is now operating, as it should. And the key selectivity feature here is that those healthy cells that are actively growing and dividing rely on different survival pathways because they need growth signals to survive, to divide. They don't have those hyperactivated SCAP networks. So when a senolytic comes in and disrupts the PI3K, AKT, BCL2, whatever, it preferentially hits the senescent cells where these pathways are maximally activated. So these are something that, work best when there's a higher burden of senescent cells. So younger organisms, fewer senescent cells, we might expect less of an impact. But in aging organisms where senescent cell burden is building or is significant, we're preferentially clearing out dysfunctional cells, which can make a really big difference. Next slide, please. So this slide is talking about a really important distinction that helps us think in a more sophisticated way about the, senotherapeutics as a whole category. Senotherapeutics is an umbrella term for all the therapeutic strategies that target senescent cells. So within that, we have kind of two main approaches. We have strategy one, which is our senolytics. That's what we've been talking about. These are our cellular cleanup crew. Their goal, kill the senescent cells. They selectively induce apoptosis to eliminate senescent cells entirely. And this reduces the senescent cell burden in the body as a result. Strategy two are the senomorphics. These are our cellular diplomats. So these don't kill the senescent cells, but they kind of tamp down those inflammatory signals. So they modulate the SASP without triggering apoptosis and suppress that inflammatory phenotype. So the senescent cells do remain there, but they stop screaming these pro-inflammatory signals all the time. So why both, right? Honestly, this is still a very open question in the field, but, theologically, we might think, just wipe out all those senescent cells, but biologically, again, more complex than that. Some senescent cells might have important functions. They maybe suppress inflammation, promote immune clearance, support tissue healing, in the right context. So killing them all off indiscriminately might not be ideal. On the other hand, if we just push down the SASP with the senomorphics without clearing the cells, then we still have cellular burden taking up space, resources, stuff like that. So sort of the emerging consensus in the field is that a combination approaches senolytics to clear, senomorphics to suppress, that remaining SASP might be optimal. So, we are doing cleanup and reducing the collateral damage kind of simultaneously. So, emerging evidence suggests that this might be the smartest. Hit those senescent cells hard periodically, but also support systemic anti-SASP signaling with compounds that, perform in that manner. But again, human data is still, evolving on a lot of these areas. Next slide, please. So I've mentioned a few times that we do have some research that's coming out about these, and it's super interesting. Most of it is preclinical evidence. These are data from animal models and other, experimental models, but it is absolutely genuinely remarkable. So I've included a few of the bigger studies on here. So back in 2011, there was a foundational study that showed when you genetically engineer mice where senescent cells are periodically cleared. So they use transgenic mice where you selectively eliminate senescent cells so the tissues don't age as quickly. Organ function is preserved longer, health span extends. And this was really huge because it provided proof of principle. The burden of senescent cells is actually causal for aging and not just correlated with it. 2015, we actually did a therapeutic study. They used Dasatinib and Quercetin. This is called the D plus Q combination. Dasatinib was a cancer medication, but they were using it like a micro dose for this, a much smaller dose. But in this study, researchers showed that senescent cell clearance alleviates frailty, extends lifespan in aged mice. And this is important because frailty is one of the most visible clinically relevant markers of aging in older humans too. So the fact that clearing senescent cells reduce that frailty in mice is extremely compelling. 2018, we had a study about neurological health. Senescent cell elimination prevented neurodegeneration in mouse models. And this is absolutely critical because neurodegeneration is another one of the hallmarks of aging that most people care about, most critically. Multiple studies show that senolytics can restore healthy function in organs like the liver, the heart, the kidney, bone tissues in aging animals. Even more impressive, senolytic treatment has been shown to counter age-related bone loss and things like that. And this matters because bone health is absolutely a major driver of frailty and disability in aging. And it's important to note that in these animal studies, these were not marginal effects. These were meaningful extensions of health span, lifespan, improvements in multiple domains of aging. And if these results translated directly to humans, senolytics would be 100% transformative. But the caveat here, and the crucial part, is that these are mice, not people. Mouse aging is not human aging. Mice have different lifespans, different tissue compositions, different immune systems. What works remarkably in a 2-year-old mouse might work differently in a 70-year-old human. That is why we now have some human trials, and that's where things get more complicated, but also more interesting. So, the animal data serves as our foundation. It's not hype. It is rigorous science showing that senescent cell burden is tractable and that clearing it has meaningful effects. But human translation is still in the early phases, and the results are much more nuanced than we see in the mouse studies. Next slide, please. So these are some of the human studies. And like I said, this is where we get real interesting, but real complicated. So we're moving from the controlled world of laboratory mice to the messy world of the reality of human physiology. So they've done some trials with some specific conditions. One of those is idiopathic pulmonary fibrosis. And this is exactly what it sounds like. This is where people's lungs start becoming fibrotic for no reason. They don't know why. So, the lungs is a tissue that needs some elasticity, has to expand and contract. So if it becomes hard and fibrotic, very bad, right? So in this one, it was a small open label trial. This means everybody knew they were getting the treatment. It wasn't blinded in terms of this design. So it's a little bit less robust, but still meaningful. And they use DQ in these IPF patients. This is very progressive, very difficult to treat, and is associated with aging. Outcomes of this improve 6-minute walk distance. And this is a standard test of physical capacity, improved walking speed. And this is clinically meaningful. Patients had measurable improvements in physical function, not a cure, but a real benefit. They also looked at a kidney disease trial. Here, researchers measured senescent cell markers directly. So they looked at the P16INK4A, which is a senescent cell marker, and they also looked at SA beta gal, which is senescence-associated beta galactoside, a very classic senescence marker. And they found that D plus Q successfully reduced the number of senescent cells in adipose tissue. And this is critical because it's, again, proof of concept that the senolytic approach works in humans. We can actually clear senescent cells in human tissues with these compounds. So this also showed us that these people had improved chair rise ability, which is another functional method, the ability to get out on a chair. Again, important part of aging and autonomy and things like that. The dosing strategy with these is also very interesting and one of the most important findings from these trials. So rather than down the hatch every day, research gave it in blocks. High dose for a few consecutive days a month and then stop. Why, we might ask? Because this maximizes clearance of senescent cells during that hit phase, and then it allows the system to recover and rebalance during the off phase. So this can potentially reduce, cumulative toxicity or off-target effects from the things that we're using. And obviously, this is a significant departure from typical supplement dosing, which is daily, and reflects a deeper understanding of biology. Senescent cells don't reaccumulate overnight, so we don't need to suppress them continuously. A periodic pulse is likely more effective and safer for the person. So, I think this is where it started moving from interesting science to actionable protocol. So, if someone is interested in senolytic support, the dosing strategy, matters enormously. Daily low dose senolytics might not achieve a senolytic effect. So, a lot of people come like, oh, I take quercetin, but they're taking, 300 milligrams or 500 milligrams once a day. It's not enough to reach the senolytic potential. So that's why these periodic higher dose strategies are what the research actually supports. Next slide, please. So this is where we're going to talk about some of those nuances and the complexity of these things, because it's really important. The D plus Q trials yielded some surprising findings that don't perfectly match the experimental animal studies mouse data that we had. So we can walk through these and talk about a few of them. One of the bigger ones was the epigenetic clocks, and these are used to measure the methylation on DNA and stuff like that. And in one D plus Q study, something unexpected happened. Treatment was associated with a transient increase in epigenetic age. So this means the cell's biological age, as measured by DNA methylation clocks, was actually appeared to accelerate transiently. And this was particularly pronounced with some of the first generation epigenetic clocks. One hypothesis as to why this would happen was that, clearing out the senescent cells might temporarily disrupt cellular composition signaling in ways that might register as aging on epigenetic clocks. These clocks are still, being refined. They're blood tests. So there's still things that are being refined and things like that. So they might not perfectly capture what aging actually is. But the important part here is that when researchers added fisetin, a polyphenol, in a follow-up study, that transient increase appeared to be mitigated. So the epigenetic age stabilized better, and this suggests a potential, synergistic effect. The other thing was telomere length. In that same D plus Q study, telomere length decreased over 3 to 6 months, which was also unexpected. Telomeres usually shorten with age. So in a senolytic, protocol, we might expect that they would stabilize or lengthen, and they didn't. A possible explanation for this was that it might be a normal aspect of immune cell turnover and activation during senescent cell clearance, or maybe senescent cell clearance might trigger shifts in cell populations that affect average telomere length. Again, much more complex than we initially thought, and so we're still trying to figure out the whys behind this. And the other one, and probably most disappointing, was about bone health. The D plus Q trial in older women for osteoporosis showed only very subtle and limited benefits compared to placebo. So this was very disappointing relative to the mouse studies, which showed very strong effects in bone density. So the takeaway here is that, human biology is extremely complex. Dramatic results in experimental models, mouse studies, things like that don't always directly translate to people. And, while we know that, clearing senescent cells is helpful, senolytics are probably not a standalone solution, for aging and age-related disease, but they are one tool in the toolkit. Just not enough to reverse kind of long-standing disease or dramatically extend lifespan in humans, at least not at the doses and frequencies that we're currently testing. But what's also true is that senescent cells are being cleared. The SASP is being reduced and some functional improvements are happening. This is absolutely real. So, this is where, intellectual honesty and things like that matters. When people ask, do senolytics work? Yes and no. They work at the cellular level because we can measure senescent cell clearance. They produce functional improvements in some domains, walking distance, chair riseability, but they're not a miracle cure. They're a precision intervention targeting one hallmark of aging. They're probably best used, as part of some comprehensive, protocol and not necessarily as just a standalone. Next slide, please. So here we're going to talk about some of the specifics in senolytics. Many of the most potent senolytics are plant-derived compounds. These are a class of polyphenols that have been screened for their senolytic activity and several have emerged as candidates. And this matters for a couple of reasons. Plant compounds are generally better tolerated than synthetic drugs. They have a longer history of use with lower toxicity concerns. They're available, as supplements, making them more accessible to people. And their mechanisms are a bit more, are increasingly well understood. Fisetin is really our champion. It was determined through studies that screened multiple flavonoids for senolytic activity to be the most potent. We find it in things like strawberries, apples, persimmons. So, it's not rare, but it's just not present in big quantities in our foods. The other one is quercetin. This is our foundational senolytic. This was one of the first plant compounds identified as a senolytic. That's why it was used in the D+Q studies. This does both, disrupts the PI3AKT and inhibits the BCL2 family proteins, but it's moderately potent, not as powerful as fisetin, but still very meaningful. We find this in things like onions, apples, capers. Again, common foods, but modest quantities in there. We also have luteolin. Luteolin is what I consider the modulator. We find this in things like celery, peppers, chamomile. Luteolin does have senolytic activity, but it also modulates some of those inflammaging pathways. EGCG, the green tea catechin, has major senolytic properties, also a very powerful antioxidants. And this is why, regular green tea consumption is often associated with longevity in certain populations. The big picture here, is that we can find senolytic compounds in everyday plant foods, and that is extremely remarkable. And it suggests that populations with high consumption of polyphenol-rich foods might naturally be getting, more senolytic activity regularly. It also suggests that senolytics aren't, something exotic. They're essentially concentrated plant extracts with refined bioavailability. And, that's important. These plant compounds, have been used for many, many years in traditional medicines and are now being better understood, on a molecular level. That said, though, the therapeutic concentrations needed for senolytic effects are much higher than what we can get from a diet. Next slide, please. And that's what we're looking at here. When people learn about fisetin, quercetin, and other senolytic compounds in food, they're like, sweet, I'll just eat strawberries and apples for breakfast every day. But the problem is that the biological actions of these compounds are very dose dependent. So to achieve senolytic activity, we need a specific concentration of these compounds in our tissues. It'd be like taking, 1 milligram of vitamin C wouldn't have the same effect as taking, 500 or 1,000. Eating small amounts of fisetin won't trigger senolytic activity. So if we take strawberries, for an example, these are one of the richest sources of fisetin in the food world. But to achieve a therapeutic dose of 160 milligrams of fisetin, you would need to consume 1,000 grams, so 1 kilogram of dried strawberries. So 1 cup of fresh strawberries weighs about 150 grams and contains maybe 3 to 5 milligrams of fisetin. So to get 160 milligrams, you would need about 8,000 cups of fresh strawberries. So, I'm not trying to be, hyperbolic here, but, this is just the math. So the reality is, while eating strawberries, very healthy, does contain fisetin, the amount is negligible from a senolytic standpoint. And so, this matters for supplementation because supplements use concentrated extract. A typical fisetin supplement, anywhere from 50, 100 plus, milligrams per serving, an amount that's impossible to get, through diet alone, really, unless you were, you would have to eat a massive amount. And, this is also why, in this sense, we talk about supplementation as separate from nutrition, because diet provides the micronutrients, the antioxidants, some low-level xenomorphic activity, from the polyphenols in foods and stuff. But achieving senolytic activity actually requires supplemental doses to be able to clear them out. Next slide, please. So we mentioned these guys already, the headliners, the fisetin and quercetin. Fisetin, again, the most potent. This is the compound from the preclinical work that clears senescent cells the most aggressively and directly. Mechanistically, it does lean hard on survival pathways like the PI3K-AKT and the mTOR pathways. So it is great to think of it as a targeted cell clearance tool for ones that rely on those. On the other side, we see quercetin, which is kind of, like I mentioned, the foundational senolytic, a bit less potent as a pure senolytic, but long history in the literature, also hits the PI3K-AKT, but also hits the BCL2 family too. Brings extra wins in the antioxidant cardiovascular support areas as well. So, this means I think of fisetin as like the sharp instrument for very focused senescent cell clearance, while quercetin is more of a broad systemic support player, especially for inflammatory and, those cardiometabolic contexts. Next slide, please. So deep dive on fisetin first. This one emerged as a leader among natural senolytics. Preclinical research consistently shows fisetin is more potent than other natural senolytics. So multiple screening studies have identified it as the most effective. As mentioned, it induces apoptosis in senescent cells by modulating that PI3K-AKT mTOR survival pathway. Specifically, it appears to disrupt those hyperactivated pro-survival signals that the senescent cells depend on. Demonstrates very high selectivity, sparing, healthy and non-senescent cells, which is exactly what we want in a senolytic. We do have some preclinical evidence for this in terms of senescent cell marker reduction, lifespan and health span extension, and, broad efficacy across multiple cell types, including fibroblasts, endothelial cells, pre-adipocytes, and other ones. We do have some clinical trials underway. A 2024 trial is investigating fisetin pharmacokinetics and safety in healthy volunteers and older people with chronic diseases. We have a phase 2 trial examining fisetin and exercise for frailty prevention in cancer survivors. There's also a 2025 study showing that intermittent fisetin improves physical capacity in aged mice. So, all these kind of hint that the effects, may translate to, humans in comparable protocols. Next slide, please. So a fisetin is our most potent. Quercetin is the most well-rounded. It's moderately senolytic, but also does some really other useful things. It was one of the first plant compounds identified as senolytic. It has the most research, has been studied extensively, good mechanistic understanding of how it works by inhibiting those anti-apoptotic pathways like BCL2 and also disrupting the PI3K-AKT signaling. It works on the same target pathways as fisetin, but with the addition of the BCL2 and is somewhat less potent. Quercetin does show moderate senolytic activity, particularly in senescent endothelial cells, the lining of our blood vessels. So, and this matters because endothelial senescence is a major driver of cardiovascular aging. Cardiovascular disease, #1 killer of both men and women. And so, that's where, some of the real value is with quercetin are those added benefits. It does more than senolytics usually do. It's a strong antioxidant, scavenges free radicals effectively. We in a longevity protocol, we want that antioxidant support and senolytic activity. So quercetin actually provides both, and beyond that senolytic activity, it inhibits the NF-kappa B, it affects the inflammasome. So it hits, some of the big hitters when it comes to inflammation. So it is helping suppress SASP from existing senescent cells, having that senomorphic activity too, plus clearing out senolytic cells. It also improves endothelial function, reduces oxidative stress in blood vessels, improves nitric oxide bioavailability. And, this is clinically important for cardiovascular health. Next slide, please. So we've talked about fisetin and quercetin, but, we have other compounds that have some senolytic and senomorphic activity too. Piperlongamine is one of those. I consider this the oxidative stress senolytic. So this one's super cool. It's an alkaloid from a long pepper, which is a spice used a lot in Indian and Asian cuisines. But rather than targeting those survival pathways like fisetin and quercetin, it selectively increases oxidative stress within the senescent cells to lethal levels. So it triggers apoptosis via oxidative stress rather than pathway inhibition. We also have oleuropein. This one has a dual action extract. So, comes from olive leaf. Very fascinating because like quercetin, it has both senolytic and senomorphic properties. So can induce apoptosis, also inhibits NF-kappa B, and the SASP signaling. So, dual action, very valuable in both doing cleanup and, tamping down that inflammatory signaling. But the classic senomorphic is resveratrol. Resveratrol is very famous from red wine, has a great longevity story. It is primarily senomorphic, not directly senolytic, but very good at suppressing SASP. It activates sirtuins and inhibits NF-kappa B, but doesn't kill the senescent cells, just quiets down some of those inflammatory signals. So the big point here is that, we have a diverse toolkit. Different mechanisms target different aspects of this, same problem. Next slide, please. So a couple more of our senomorphic friends here. Apigenin, this is the NF-kappa B inhibitor. This is a flavonoid found in high concentrations in chamomile, parsley, celery. It's, again, specific inhibition of NF-kappa B, which is that master regulator of inflammation and SASP gene expression. So specifically, apigenin prevents phosphorylation and nuclear translocation of some of the key signaling molecules that perpetuate SASP. So by doing that, it shuts down SASP gene expression. So, the senescent cells are screaming inflammatory signals via that NF-kappa B, and apigenin is coming and, tying on the gag on that signal. The signals are still there. The cells aren't being killed, but that noise is being suppressed. In this category, we also have camphorol, which is a vegetable senomorphic. Find this in things like kale, broccoli, capers, also in tea. It works similarly to apigenin with inhibiting NF-kappa B and the SASP. So, using both of them is ideal because, the senolytics have limitations. They work best intermittently in that hit and run protocol. So between pulses, senescent cells aren't being cleared, but they're there making the SASP. And that's why the senomorphics are there to provide that continuous support and suppress the SASP continuously, reducing inflammation while we're waiting for the next senolytic cycle pulse. Next slide, please. So that's, where the power of synergy kind of comes in. Do we need to take senolytics individually? Are the combinations better? And, the key insight here is that senolytic cells are not uniform. Senescent cells are not all the same. They're triggered by different stressors. They occur in different tissues. They rely on different survival pathways. So a senescent cell in the lung might heavily rely on, PI3-AKT pathways versus a senescent fibroblast in the skin might rely on BCL2. An endothelial cell might rely on a combination of both. So the problem with single senolytics, if we're just using fisetin, we're primarily targeting the PI3-AKT-mTOR pathways. So stuff that relies primarily on BCL2 isn't getting touched by fisetin. Fisetin might not kill it. So that's why, formulas that combine multiple senolytics, fisetin, quercetin, and even some of the senomorphics, apigenin and things like that all together, provide broader coverage, enhanced efficacy. And, combining both of them means that we're cleaning up and suppressing, in the same comprehensive formula. These also allow for lower individual doses. So when compounds work synergistically, we can achieve the same effect with lower doses of each individual compound, and that reduces the risk for off-target effects and toxicity kind of things. Next slide, please. So we've mentioned the hit and run dosing several times, and this is one of the most important factors with using senolytics effectively. So if we take a low dose of a senolytic every single day, we might not actually achieve senolytic activity because we're not getting a therapeutic level into the bloodstream. We'd be getting steady low levels, but senescent cells, wouldn't be experiencing the biological stress needed to trigger that apoptosis. And that's why we utilize this hit and run strategy. So instead of daily dosing, people can identify what cycle they want to use. Might be monthly, might be quarterly, might be twice a year. For someone that's younger, in their 30s, maybe they only need to do it twice a year. For someone that's in their 70s, they might want to do it once a month. It just depends on the person. There's no sort of hard and fast rule for that. And they can make their cycle. But during that hit phase, that's when they take the high dose of the senolytic or combination. And these are usually for anywhere from 2 to 5 days. And then during the recovery phase for the remainder of the time, you don't take anything. And that's, what we're showing here, a pulse concentration dose during those days, and then nothing until it repeats. And this works because it maximizes impact and minimizes exposure, and it works with biological timing of the body. It takes weeks for senescent cells to reaccumulate to problematic levels after a clearance event. So we don't need to suppress them continuously. These kind of monthly or quarterly or whatever pulses are, theoretically sufficient in that regard. Next slide, please. So, to kind of ground everything that we've learned today, senescent cells accumulate with age. They drive chronic inflammation. They drive tissue dysfunction. This accumulation is tractable. It's actionable. We have compounds that can selectively clear out these cells. This mechanism is understood. We know how senolytics work. They disable those survival pathways that senescent cells depend on. Preclinical evidence, compelling. Animal models, clearing senescent cells extends healthspan, lifespan, improves organ function. Human evidence is emerging. We have proof of concepts that senolytics work in humans, and we can see functional improvements. But human biology is super complex, and mouse results haven't translated one-to-one. But senescent cell clearance is still helpful, in mitigating some of the aging process. So, I think of this as, something that is really important to kind of deeply understand, and it really enables us to help people make informed decisions about aging. So, this is something that is grounded in real biology, and, that's a powerful thing. The future of medicine, I don't see it as, something where we're just treating disease in the elderly. It's about managing cellular aging in real time, and intervening in these mechanisms of aging before they become diseases. And senolytics are a prime example of that future that's available right now. Use them wisely, explain them clearly, integrate them into comprehensive protocols. And that is how we stay on the leading edge of wellness and health. So thank you guys so much for joining me today. I hope that was helpful and good information. Thanks.
Thanks, Andrea. We have a couple questions. One I'm going to ask, and then I'll ask a couple that came in. For the study, how much fisetin did they use?
160.
160 milligrams, the same as the weight you showed.
Mhm.
Okay. And how much quercetin?
That varied. Some of them were 500, some were 300. It just kind of depended.
Okay.
And even up to 1,500, depending on how they were dosing it. If they were doing some studies that use quercetin by themselves, used higher doses.
Such as?
1,500.
1,500. Okay. Okay. And then there was several or a couple that asked about fasting. Can fasting have the same effect and be a senolytic?
I have not seen research to that.
Okay.
That supports that. I don't know that fasting acts on those senolytic pathways that the SASP pathways that way. So I have not seen, but that's interesting. I haven't seen research on it though at this point.
Well, and I think the question comes too because, fasting has shown to improve longevity, right? So that was, I think that's where the question's coming from. So.
Yeah, intermittent fasting definitely, from that aspect for sure.
Right.
I think we have good research for that.
So, okay, I think that was all the questions. And is there a formula? I guess one question I would have, is there a company that does the formulation of
There are
all
many
okay.
companies. Some of the good ones that I like, Pro Health makes a good one. It's a rapid reset multi-senolytic. It's got 11 different senolytics in there. That one's probably one of my favorites. Qualia also makes a good one. Those are two companies that are really longevity focused companies. And so they really focus on making sure that you're getting the amounts in there that are from the research.
Okay, great. Thank you.
Mm-hmm.
Anything else you want to add before ending?
No, I think we're good. Thank you, guys.
Thank you, everyone. We'll be sending out an email follow-up with the link to the recording and the slides that you can download.
Perfect. Thank you.